Okay, so we'll talk about thermal expansion of solids. So let's say you have a metal bar which has a length capital L. Now it has been observed that if you let's say the temperature at which this bar is maintained is T1. But let's say if you increase the temperature from T1 to T2, it has been observed that the new, let's say the initial length is L1 and the new length is L2, and if you increase the temperature such that T2 is greater than T1, it has been observed in most of the cases that L2 is greater than L1. And this is called the thermal expansion of solids. And it has also been observed that the change in length, which means delta L, equals, which is L2 minus L1, it's not really L square but L2, is proportional, which means it increases proportionally with temperature, increase in temperature, which is delta T. And we know that delta T is nothing but T2 minus T1. That's the first observation. Moreover, it has been observed that delta L is actually also proportional to to initial length L1, which is just L1. So in a way you can say that delta L is proportional to the change in temperature delta T multiplied by the initial length, let's call it L now, of the rod. You can remove the proportionality constant by including the proportionality constant alpha, and and this is what we get. Let's call this Li, which means L initial, the initial length of the rod. Now this is an experimental observation that more or less solids follow this kind of behavior. Alpha is called coefficient of thermal expansion, well actually linear expansion, because you see it's proportional to linearly to the temperature as well as the length, so it's called coefficient of linear expansion. Okay. Also, the same thing can apply to volume. This, instead of length, let's say if you have area or volume, let's say if you have, actually I should have chosen a black color, but somehow I chose the red one. And if this guy, which is a square plate, is resting at temperature T1, and if you increase the temperature, the area of the plate increases. Similarly, if there is a volume something like this, then this volume also increases. Well, I'm really exaggerating everything, but I'm just trying to give you an idea. Sorry for the bad drawing. So the volume also increases if we increase the temperature. Now, as you can see, we can relate these things. First of all, we can write very similar to this. We can write the same thing here, where we can write the delta V. Let's talk about the change in volume. In this case, is gonna be beta is the new proportionality constant, the change in temperature multiplied by the initial volume of this. And again, that's again an experimental observation. It's not really that has been derived theoretically, it actually has been observed. And also we can actually relate beta with alpha, and to do that we can actually let's say how to do that. So we know that delta L equals alpha delta T Li, let's call the initial length. We also know that delta V equals nothing but beta times delta T times Vi. Let's assume we have a cube void, and let's say the length is L, the width is W, the height is H. So we can actually write the final V, let's say Vf, after temperature has been increased, as L plus delta L, H plus delta H, and W plus delta W, which gives us L, H, W, plus, actually what we get is 3 alpha delta T plus 3 alpha delta T square plus alpha delta T cube. Now we know how do we get alpha, because we know that delta L is nothing but Li delta T times alpha. Similarly, we know that delta W is nothing but alpha Wi delta T, and similarly we know that delta H is nothing but alpha Hi delta T. After we substitute this, we actually will be getting something like this. So this is nothing but Vf equals Vi 1 plus 3 alpha delta T plus 3 alpha delta T squared plus alpha delta T cube. Well, alpha is actually, in real life, you see that we'll find that alpha is actually a very small number. So alpha delta T is actually also a very small number. For, let's say, delta T of the order, say, 100 degrees centigrades. In that case, we can simply ignore this part because it's very small compared to the first two, and simply write Vf equals Vi plus 3 alpha delta T Vi. Now we know Vf minus Vi is delta V equals 3 alpha delta T Vi. Now as you can see, we can compare it with the formula we were using here, and we can see that beta is very close to 3 alpha. So this is actually the most basic formula which can be used. You can actually use it for seeing when we have problems relating in area. And as you can see, I used a cuboid here, but any volume can actually be broken in many cuboids. So this formula actually always holds true in terms of any volume. And beta is actually called coefficient of volume expansion. So that's about it. This is all about expansion of solids as you increase the temperature. There have been many applications of this phenomena. You can find on the internet, but I mean this is something which is used often in many things. As a matter of fact, let's say a simple rheostat. Well, actually, let's say we have this temperature regulating devices. So the way the temperature regulating devices work is, let's say you have a positive voltage providing circuit. You actually have a strip kind of thing, metal strip, which is actually connecting the plus with the minus, so that the connection is completed, and you have this heater somewhere here, which is a resistor, and which is heating up the whole thing. And let's say this is room, and if you increase, and if the room, because of this heater, there'll be heat coming out, and this heat will actually heat the room, and the temperature of the room will increase. Now the way this strip is designed is that it consists of two different metals which have different alphas. So they expand differently as temperature delta T is increased. So what happens, this metal strip actually curves because one of the metal expands differently than the other one and breaks the circuit. So as it breaks the circuit, there's no more heat, there's no more current which is going in that resistor, and the room starts cooling down again. As the room starts cooling down again this skewed shape becomes a straight shape, and again the circuit is formed and the heater starts working again. So that's one apparatus where we can see the use of this thermal expansion of solids. We'll talk more in the other classes.